So welcome to this video on revision worksheet 19. So this revision worksheet contained 3 questions. So 2 from the 2018 DEB Mock, both from paper 2, question 1 and question 5, and a question from the 2017 DEB Mock, which was from section B, so it was a longer question, and that was question 8. So the first 2 will are worth 25 marks each, and the last one was worth 50 marks. So let's get started. So question 1. Orla and Liam play a game that consists of tossing an unbiased coin. The first person to get heads is the winner. Orla tosses first. If Orla tosses first, find the probability that Liam wins the game on his first toss. Okay, so with these probability questions, generally they're not too difficult mathematics-wise. However, often the logic around it is what upsets people. So if Liam wins the game, we have to think of what happens. So then what has happened is the probability that Orla has played and Orla has gotten a tail, so she hasn't won. And then Liam plays, but he wins, so he gets heads. So if they each are playing with an unbiased coin, the probability of getting either heads or tails is a half, so these are both halves. And the word "and" when we're talking about probability is multiply. So we end up with a quarter, which is 0.25. So the next question asks that Orla wins the game on her second toss. So this time Orla, the first time, gets tails. And then when Liam plays, he also gets tails because he doesn't win this time. And then now we're on Orla's second toss, Orla will get heads. So she'll win. So we'll get a half. Multiply, because it's the word "and", a half, multiply the word "hand", and a half. So that is 1/8, or in decimal form 0.125. Now, both of those quite straightforward. And this third part here, just to make a little bit of a note, it uses a geometric sequence. Now, I'm going to go through this anyway, just so you can see what happens. If you have your log tables in front of you, that will be very good. So what's the probability that Orla wins the game? So there's so many different ways that Orla can win the game. So if she won it on her first toss, basically the probability of that happening is a half, because she tosses first. She's half a chance of getting heads, half a chance of getting tails, so she's half a chance of winning. Or, now the word "or" here is a plus. So we've already worked out that she wins on the second toss, and that works out to be 1/8. Now, if we were to go again and try to figure out, well, what would be the probability of her getting on the third? Okay, so on the third, she would lose, then Liam would lose, then she would lose, then Liam would lose, then she would win. Okay, so what we end up is equal to 1 to the power of 5, which is equal to 1/32. Now, and that goes on. The next one will be actually 1/128, because it'll be 2 to the power of 7, and so on. And that will go on forever, because she could keep getting tails forever. Now, chances are she won't, but she could. So this goes on into infinity, okay? And what happens is we now have what's called a geometric sequence. This is a sequence where each term is the previous term multiplied by some number. So to get from a half to an eighth, I multiply by a quarter. To get from an eighth to 1/32, I multiply by a quarter. And to get to 1/32 to 1/128, I multiply by a quarter, and so on. So if you go to page 22 in your log tables, this is a sequences in series page, and you should have seen this before, just looking at arithmetic sequences for junior cert. Now, geometric sequence is kind of like an exponential, so it's going up with a multiplication. There's a power there. So we've seen something to this. However, if you want to get the sum of a sequence, you have 2 formulas here on page 22. The first one is the sum of the first n terms, and that is Sn. However, in our case, we have infinite numbers, so the sum to infinity. So the formula is the sum to infinity is equal to a over 1 minus or. Now, we have a lot of bits of information here. So in order to use that formula, we need to figure out A. According to page 22, A is the first term. So for us, that's a half. It then is 1 minus or, and or is the common ratio. Now, this thing that we've worked out here, this is our common ratio. So what we would have had when we worked with our arithmetic sequence is a common difference. Okay, so what do you have to add each time? Here's common ratio. What do you have to multiply each time? So our common ratio is a quarter. So let's go back to our formula. The sum is going to be a half divided by 1 minus a quarter, and you can stick that straight into your calculator and work through it, or you can work through it yourself and simplify down. We should get 2 over 3. So the chances of Orla winning the game is actually 2 over 3. So that is depending on how many times they have to play. We've taken all scenarios into account. So that's a nice question which kind of combined something straightforward with the probabilities with a little bit of sequences and series. So part B then said, a game of chance comprises of a player spinning a lottery wheel. There are 100 positions in which the ball has an equal chance of landing, but there's only one chance for a player to win the top prize. Okay, so from that, so for one toss, if you want to win, the probability of winning is 1 in 100, and the probability of losing, okay, actually I'm going to say not win, just so we can keep to this idea, not win. So you either win or you not win, and that's going to be 1 minus 1 over 100, which is 99 over 100. Okay, and that here is for one spin. Find the minimum number of spins that Karina must attempt in order for the probability of winning the top prize at least once is no less than 25%. Now, there's a lot going on here. At least once. So they want to win it and no less than 25%. So when you're dealing with at least once, it's basically not winning, if that makes sense. So the chances of me winning at least once is the same as me 1 minus probability of me not winning at all. So we need to figure out, well, how many times does she need to spin it? So let's call this number of spins n. So she wants to spin this so many times. So if she never wins the prize in all of her spins, so the probability of her not winning on one spin is 99 over 100. But in all n spins, this is going to be to the power of n. So now that I've worked out the probability that she'll win at least once, so just break this down. So this is the probability she will not win at all. So 1 minus that will give us the probability that she will win at least once. And it's important that you understand how to work with that at least. So they tell us that this probability, we want this to be no less than 25%. So we're going to let this equal 0.25 for a minute. So let's take the formula 1 minus 99 over 100 to the power of n equal to 0.25, and let's work with that. So we get 99 over 100 to the power of n is equal to 0.75. Now, we need to work out what that power is, and in order to do that, we're going to use logs. So anytime that we have a power that we don't know or that is an unknown, we're going to use logs. So let's rearrange this. We get log to base 99 over 100 of 0.75 is equal to n. This can go straight into our calculator and we get 28.62 spins. Now, obviously we can't have a fraction when it comes to spins. This case, we're always going to round up, because if we don't round up, the probability is going to be less than 25%. So it's really important that even though in this case we would have rounded up anyway because it was 0.6, if this was 0.4, we would still round up. So she needs to have 29 spins to have no less than 25% of winning the top prize at least once. So question 2. A jury of 12 people is to be selected from a panel of 8 men and 8 women. In how many ways can the jury be selected? So this is working with combinations, so permutations and combinations, so that chapter there. So this generally comes just before probability, and it can get quite confusing, but it's important that you're able to work with it. So we have 12 people that have to be selected from a panel of 16. So we have what is 16 choose 12. Now notice these brackets, there's no line, it's not a fraction. This means 16 choose 12, and you should be able to find the choose on your calculator. If you have a Casio calculator, it's just above the divide sign. So putting this into the calculator, you should get 1,820. So that's the number of ways there are of picking the jury without any kind of restrictions. It's the restrictions that kind of cause these questions to become a little bit more complicated. So then it said, find the probability that the jury selected has more women than men. Okay, so let's look at this. So if there's more women than men, so what would happen? So we have two options. So option 1, that there's 7 women and 5 men. Option 2, there was 8 women chosen and 4 men chosen. So from the 8 women, 7 were chosen. So we had 8 choose 7. And the word and always means multiply. 5 men, we had 8 choose 5. Or the second option. The word or always means plus for us. We have, sorry, now let's clean up my brackets. So we have 8 choose 8, and, so that's multiply, 8 choose 4. And working that out, we get 8 choose 7 multiplied by 8 choose 5 plus 8 choose 8, 8 choose 4, and working that through, you should get 518. Now, that's the number of juries. So, number of jury selected with more women than men. So, to work out the probability, it's going to be 518, the number of those, over the total numbers of juries that can be chosen, which simplifies down to 37 over 130, which gives us 0.284615. Now, they didn't specify how they wanted the probability or rounding, so I would just leave them in both the simplest form of a fraction and then the decimal. So a maths teacher tells their class of 23 students that there's a greater than 50% chance of two or more of them having the same birthday. Do you agree with her? Justify with a calculation. So 2 or more. So if 2 of them have the same birthday, 2 or more, that's another way of saying at least 2. Now, if one person has the same birthday, it's the same birthday as what? So this is actually the same as 1 minus the probability that none share their birthday. Share the same birthday. So what's the chances of all 23 students having different birthdays? Well, so let's work down here. So let's see. If I take the first student and I say, well, you know, when's your birthday? So the chance of them having that birthday, well, there's 365 days to choose from. So that's fine. The next student, now, if they want to have different birthdays, now they only have 364 days to choose from. And the next student just has 363 days to choose from, 365, and so on, down 23. So we have 344 over 365, and 343 over 365. So that's the probability that they all have different birthdays. And when you work that out, it works out as 0.492702, and that works out as 0.507279, which is about 50.7%. So was the teacher correct? Is there a greater than 50% chance of two or more of them having the same birthday? And yes, therefore the maths teacher is correct. Now remember, if you have two or more of them having the same birthday, you can work out what's the chance of two of them having the same birthday, three of them having the same birthday, and so on. But actually that's a lot more complicated. It's much easier to work out the one way that they all have different birthdays and saying, well, that's going to be 1 minus that probability to get our answer here. So question 3. So this is the longer question. It is more linked with it is a problem-solving question, 50 marks, coming from the section B of the paper. So figures on the number of people passing the driving test are published annually. On analysis of the data, a researcher found that the probability of a person passing his or her test in a particular test centre on their first attempt was 2 out of 3. 6 individuals are taking their test for the first time. Find the probability that at least one of the individuals passes the test. Now, this is important. There's 6 people. We just want at least one of them to pass. We don't care in what order that happens. And when there is no order, we use something that's called the Bernoulli trials. Now, if you have your log table set in front of you and go to page 33. So going to page 33, just down the bottom, underneath probability distributions, we have what's called a binomial distribution here. And that formula is the one we're going to use. So we have n choose or, p to the power of or, q to the power of n minus or. And what do all those letters mean? Well, n is the number of experiments or the number of iterations that this is going to happen. So we have 6 individuals, so n is equal to 6. Or is the number of times that we want success. Okay, so success for us here is that it passes that one at least, now we'll look at that word again, at least one of the individuals pass the test. So what we're going to do is actually 1 minus the probability that none pass the test. Okay, because that will get us the idea of at least one passing. So we're actually going to work that nobody passes. So or in our case is going to be 0. P is then the probability of passing. So they've already told us that passing it on the first attempt is 2 over 3. And Q then is the probability of failure or not passing, which is 1 minus 2 over 3, which ends up being a third. So let's work with this. So we have 6 choose 0, 2 over 3. Notice the difference of 6 choose 0 rather than a fraction to the power of 0 and a third to the power of 6. So putting that into the calculator, 1 over 729, just to remind you, this here is 6 choose 0. Okay. So I want to figure out then the probability that at least one pass the test. So 1 minus the probability, well, that none of them pass the test. So that's 1 minus 1 over 729. So the probability that at least one of them passes the test is 728 all over 729, which if you want to leave it in decimal, 0.998628. Find the probability that at most 4 individuals pass the test. So you have 2 options here. You can work through that nobody passes, 1 passes, 2 passes, 3 passes, 4 passes. So that's doing binomial or this Bernoulli trials 5 times. The other option is we can do the idea of 5 passing, 6 passing, and taking them away from 1. So you have to get kind of smart while working with all these probabilities and do it in the easiest way possible. So we're going to do probability that 5 pass, or the probability that 6 pass. Okay, actually I should square up my brackets here. And again, we're using Bernoulli, so it's going to be 1 minus. This is going to be 6, choose 5. So we do 6 tests. Well, there's 6 individuals, and what's the chance of 5 of them passing? So again, 2 over 3 is probability of passing. We want this to be 5, and a third to the power of 1. Or always means add for us, and then we have 6, choose 6. 2 over 3 to the power of 6, 1 over 3 to the power of 0. So working those out, we should get 192 over 729. So that's the probability that all 5 of them pass, and the probability that all 6 of them pass is 64 over 729. So working that out, that should work out as 473 all over 729, and that should equal 0.648834. Again, so we've done their Bernoulli twice. You can do Bernoulli 5 times. So it's just about getting really, smart. And before you work through a question, think, okay, so maybe the first way I think of is working out that the probability 0 pass, the probability 1 pass, 2 pass, 3 pass, and 4 pass. But is there an easier way? Now, you should get the exact same answer if you do it that way, but you have to try and work as efficiently as possible through these papers. So if you are working it, or if you did work it the longer way, just to make note of this, not shortcut, but this more efficient way to work. So a little bit of hypothesis testing here. Now, this hypothesis test is based on proportion rather than mean. So we don't see that as much coming up in the actual papers, or we haven't seen it yet. I suppose hypothesis testing hasn't been on it long enough for us to really make a judgment on this. So it's a really good question to see. So a reputable driving school claims on their website that 80% of its students pass their driving test on the first attempt. So this is important. So this is their claim, 80%. So that is the proportion. Okay. So we call that our P, 0.8. In order to test this claim, a sample of 900 people, so now they're talking sample, N is equal to 900, who use the school and who had taken their test for the first time are chosen at random. The number of people who passed is 675. So using the sample, the proportion of the sample who passed was 675 over 900. So we need to work that out ourselves. And when we do that, 0.75. Now, our proportion as given by the sample is not the same as the proportion that they claim, so i.e. our population proportion, but we can use hypothesis testing to see whether that sits within a reasonable frame for us to decide whether to accept or reject their claim. So, conduct a hypothesis test at the 5% level of significance to decide whether there is sufficient evidence to justify the driving school's claim. Write the hypothesis, and write the null hypothesis, alternative hypothesis, and state your conclusion clearly. So the null hypothesis. So they've claimed that the probability, the proportion is 0.8. So what that means in words, okay, and then the alternative hypothesis does not equal 0.8. So what that means in words, so for the null hypothesis, the percentage of students who use the driving school pass their driving test on their first attempt is 80%. So for the alternative hypothesis, the percentage of students who use the driving school pass their driving test on the first attempt is not 80%. So if we accept the null hypothesis, we're basically saying yes, their claim is correct. If we reject the null hypothesis, we're saying their claim is incorrect. So in order to test that, we're going to use the confidence interval. Okay, so we're going to use a confidence interval. And there's a few different confidence intervals that we use. So the one we're going to use is for a population proportion. Proportion P. And our formula for this is one that you need to know. So if I want to work out the P, it's going to lie somewhere between P hat, P plus or minus my z, which is 1.96, and I'm getting that from my 5% level of significance, the square root of p hat 1 minus p hat all over n. So what that works out for us is 0.75 plus, sorry, I'm actually going to turn it into we're going to turn it into range of values. So I'm going to work with minus 1.96 here. The square root of 0.75, 1 minus 0.75, all over n, which is 900. And that should be less than or equal to my actual proportion, which should be less than or equal to 0.75 plus 1.96 square root of 0.75, 1 minus 0.75, all over 900. So I create this confidence interval where I can then decide whether my p sits in there or not. So when I work that out, it should work out as 0.72171, which is less than or equal to p, which is less than or equal to 0.77829. So based on the sample that we did, we can say with 95% confidence that the actual proportion lies somewhere between 0.72171 and 0.77829. However, because 8 does 0.8 sit in there, so no, it does not. So what we would say is 0.72171 is less than or equal to 0.8. However, it is not less than 0.77829. Therefore, we reject the null hypothesis. Okay. So that means that we're saying, well, actually, we don't believe that their claim is correct because based on that sample, their claim should sit somewhere between 0.72 and 0.77. So last thing we need to do is the conclusion, and the conclusion should always link back to the question. So we would then say, therefore, the driving school's claim is incorrect. Or you could say that there is not sufficient evidence to justify the driving skills claim. Anything like that. Link it just back to the driving skills claim. So this is a nice follow-on part of that question. So it said, find using the 5% level of significance the least number of people in the sample required to pass their driving test in order to accept the driving skills claim. So this time we're actually going to work the other way. We're going to still create a confidence interval. So we're going to create a 95% confidence interval. However, this time we're actually going to use it to figure out, instead of the population proportion, we're going to use it for the sample proportion. So basically anything we did on the last slide, we're basically going to end up reverse it. So instead of p hat plus or minus, we're just going to have p plus or minus. Again, we're using 1.96 because it's 95%. Square root of p bracket 1 minus p all over n. So it looks just like our last formula, but all the p hats have been left as p. So when we work this out, so our p is going to be 0.8 and our n is going to still be 900. So we end up with 0.8 minus 1.96 square root of 0.8 bracket 1 minus 0.8 all over 900 is less than or equal to p hat. So we've actually worked the other way, and we've said, well, look, we are going to work with the actual proportion or the actual claim that they have and see can we work backwards. So working very similar to the last time, 0.8 1 minus 0.8 all over 900, and for us that works out as 0.773867 is less than or equal to p hat, the sample proportion, 0.826133. So if our sample proportion had been anywhere between these two numbers, then we would have been able to accept the driving skills claim. But they want the least number of people, so the smallest number. So we are going to actually use this proportion here. So basically what we're going to work out is 0.773867 multiplied by 900 to find how many people that actually turns into. And when we get that, we get 696.48 people, but obviously people can't be part, so 0.4 of a person doesn't work. And we're going to have to round up, because if we round down, we wouldn't have exactly hit that proportion, so we wouldn't have actually accepted it. We would have been very close, but we wouldn't have accepted it. So we need to round up in this case. So we end up with 697 people. So that's how many people in the sample of 900 would have to say, yeah, I passed my driving test the first time, in order for us to say, yes, the schools claim is correct, or we have enough evidence to support the schools claim. So in a random sample of 200 drivers from all parts of the country, a 95% confidence interval for the mean of penalty points received was between 4.1921 and 46079. So that's the mean of the whole population, mu. If we were dealing with the sample mean, it would be x bar. So let's take a look at how we would work with this. So this is such a nice question in the sense that it asks so many different things, and we see 3 different confidence intervals used. So this time we're going to work with a confidence interval for the population mean. So we're going to work with the population mean. And what we're going to work for that, the formula is x plus or minus 1.96, because it's 95%. Standard deviation over root n. Now, here's the thing. Sorry, that should be x bar. We do not know x bar. We do not know the standard deviation. We do know n, because that's 200. And that's literally it. So let's work this out. We get x bar plus or minus 1.96. Oh, sorry, I'm actually going to turn this into we're actually going to turn this into the range of values. Sigma over root 200 is less than or equal to mu, is less than or equal to x bar plus 1.96 standard deviation over root 200. Now, we know that this is 4.1921 is less than or equal to mu is less than or equal to 4.6079. So what we've actually created here is 2 little equations. The first equation is, I know x bar minus 1.96 sigma over root n, root 200. That actually equals 4.1921. And the second equation is x bar plus 1.96 standard deviation over root 200 is equal to 4.6079. Now, I have 2 equations, 2 unknowns, so what I'm using is simultaneous equations, and I'm going to work with elimination. So I'm going to eliminate something. Now, these eliminate straight away because I have a plus and a minus, and I'm left with 2x bar is equal to, adding these together, it gives me 8.8. So x bar is equal to 4.4. Now that I've worked out an x bar, I can go back and work out the standard deviation, which is what I wanted. So using equation 1, I get 4.4 minus 1.96 standard deviation over root 200 is equal to 4.1921 minus 1.96 standard deviation over root 200 is equal to 4.1921 minus 4.4. So sigma is equal to, when I take those away, so what I'm going to do is I'm going to have root 200 times 4.1921 minus 4.4 all over minus 1.96. So sigma is going to work out at 1.5. So really interesting, like a really interesting question here that has kind of given us the confidence interval and working back, and you think, well, they've actually given us no information, but it's this idea of being able to use simultaneous equations to work them out. So actually really, really interesting question. So the very last part of this question is how many drivers in this sample can be expected to have more than 7 penalty points? So what's the probability that a driver has greater or more than 70 penalty points? Well, I can't work out that probability, but what I can do is I can convert that to a z-score. So I get x minus x bar all over sigma. Now, my x in this case is 7. My x bar from the previous part is 4.4. My sigma is 1.5. So my z is equal to 7 minus 4.4 all over 1.5. And when I work that out, I get my z is equal to 1.73. Remember, the log tables can only go to 2 decimal places anyway. So now I'm going to replace my numbers here. So my x is replaced with z, my 7 is replaced with 1.73. So I get 1 minus the probability that z is less than 1.73, less than or equal to. So we can't get the greater than, because remember our tables, and in this case we're looking at page 36, our tables only work towards the left. They're only working where it's less than. So I have to convert this to less than. Now I can look up my tables, and I look up 1.73 in my tables, and I end up with 0.9582. And when I take them away, I get 0.0418, and that equals to 4.18%. So I know that 4.18% of the sample have 7 or more than 7 penalty points. But they asked how many drivers this is. So I need to get 4.18% of the 200 drivers, and that works out for me as 8.36. However, I need to round up when I do this. If I don't round up, I won't have hit more than 70 penalty points. I would just be below it. So just be really careful with your rounding, especially in statistics, because what we might often find is we have to round up regardless.